I can start.
Okay, so hello everyone, welcome to the European Non-Associative Algebra Seminar. I'm going to introduce the speaker of today, Jari Desmet from Ghent University, Belgium. And he's going to talk on Jordan algebras and automorphism groups of Matsuo algebras. Please.
Okay, so first of all, thanks to the organizers for inviting me to speak here. And of course, as the name of the seminar, I'll talk about some non-associative structures that I think are interesting, and I hope I'll be able to convince you that they are interesting as well. So the context I work in is axial algebras and essentially idempotents in non-associative algebras. And I'll just give a brief overview, or actually quite an extensive overview of why I care and maybe why you could care as well. And then I'll tell you exactly what Matsuo algebras are, how they're related to Jordan algebras, and why the automorphism groups or studying the automorphism groups of these objects might be interesting. So that's kind of the plan for today. First off, everything we do is with algebras over a field. We'll ask that the characteristic of the field is not 2. This is going to be, this is kind of intrinsic to the context I work in. If you want to, you can try to come up with some definitions where this characteristic condition is not necessary. But for now, it fits the framework. And later on, I'll actually also have to assume characteristic 3. I will give some reasons as to why this might be, but essentially I can get rid of the assumption that the characteristic is different from 3. But there are some good reasons to assume that the behavior there is quite different. Anyway, the first definition we're going to give is that one of the Jordan algebra. I assume that most people here know what a Jordan algebra is. In some sense, you could say they're the second most well-known class of Jordan algebras. The first one, of course, being Lie-algebras. But just for in case, it's a non-associative commutative algebra over a field with the characteristic 2 that satisfies this polynomial identity. So it's essentially, you can think of it as a sort of weakening of associativity. Associativity says that the multiplication operator of any 2 elements commute. And here we actually say that actually the commutator of the multiplication operator Lx and Lx squared has to be 0. So it's saying that specific elements should commute. This is the way you can think of it. Of course, for a small example, as most of you probably know, if we take any associative algebra and we try to deform the algebra product into something commutative by just saying I'm gonna take the sum of A times V and B times A, then normalizing by adding this 1/2, then I get a Jordan algebra. This is sort of the easiest case of Jordan algebras, and then of course algebras that are Jordan algebras that are subalgebras of these kind of objects are called special, and then you have the exceptional Jordan algebras, and so on. But this is not really, I'm not a Jordan theorist, so this is not really what I'm going to do. What I care about is idempotents in Jordan algebras. And for that, we need to introduce some notation. If we have any algebra, either associative or non-associative, Jordan, Lie, whatever, and any element A, we can always write or think about left multiplication by this element as an operator. So left multiplication by this element is an operator, and then asking questions about this operator are kind of trivial in the sense that you want to know what the spectrum is, you want to know what the eigenvalues are, how the eigenspaces maybe interact, and that's what we're going to try to do. For that, we note the lambda eigenspace of the left multiplication operator as a lambda of A. The easiest example is, of course, when A is associative, and then we can take A to be this little a to be an idempotent. Of course, I already said I care about idempotents. If you take little a to be an idempotent, then the spectrum of this multiplication operator is always 0 or 1. Where I should probably write actually that it's contained in 0 or 1, you can write down, like if you just take the unit, then it has no 0 eigenspace. But why is this the case? Because you can easily write down that A times V is on the one hand, where V is a lambda eigenvector, is on the one hand equal to lambda squared of V, but on the other hand, it's also just equal to AV, which is equal to lambda V. So this tells you that over a field, the only possibilities are that either lambda is either 0 or 1. And then more generally, you can also say that A0 and the 0 eigenspace and the 1 eigenspace are both subalgebras, and they have to be orthogonal. This is kind of telling you that idempotents decompose your algebra into smaller parts, which are easier to handle. And back in the 40s of the last century, I mean, this is also something that was noticed for Jordan algebras, this sort of Peirce decomposition. So it was Adrian Albert, that noticed that if you have a Jordan algebra and an idempotent in this Jordan algebra, that the left multiplication operator is diagonalizable with eigenvalues 0, 1, and 1/2. So there's just one more eigenvalue popping up, which is quite surprising because you don't have this associativity that you can use. You can still use the polynomial identity. And then we still have that the 0 eigenspace is a subalgebra. Oh, excuse me. That the 1 eigenspace is a subalgebra. That they're orthogonal subalgebras. And then this 1/2 eigenspace plays the role of some sort of absorbing element for the 0 eigenspace and the 1 eigenspace. And if I square the 1/2 eigenspace here, then I end back up in the A0 and the A1 eigenspace. And in some sense, this is like the smallest thing you can get for such a diagonalizable non-associative algebra with idempotents. Small example, suppose we take the 3x3 symmetric matrices, and we take our favorite idempotent. We know idempotents are just rank 1 matrices. My favorite one is just the 1 in the first entry I see and 0 everywhere else. Then it's fairly easy to see, and you can just work it out as an exercise, that the eigenvectors of eigenvalue 1 are precisely of this form. The eigenvectors of eigenvalue 1/2 will precisely be these of this form. Why is that? I mean, you can just see, but essentially, if I take A times B plus B times A, then only one of the two will be non-zero. So if I take 1/2 E 1 times V plus V times E1, then either this is 0 or that is 0, and that's why you get a 1/2 appearing there. And then here, because you have no, they don't share a column or a row, these entries, these will also always be in the 0 eigenspace of this idempotent. That is something you can easily see. So that's kind of, that tells you that at least the eigenvalues are correct. But then if you do the same for E2 and E3, where E2 is the matrix with just the 1 on the the second diagonal position, and E3 a matrix with only a 1 on the third diagonal position, then you can see that this really separates the matrix entries in some sense, in the sense that if I take the intersections of eigenspaces, then the intersections will be at most one-dimensional. And E1, E2, and E3 have commuting multiplication operators. But this kind of tells you that just from these idempotents, I can kind of reconstruct the matrix entries. And this is formalized in the so-called Jacobson coordinatization theorem, where I've written some vague result here, that any unitary Jordan algebra with sufficiently many idempotents, this, take it with a grain of salt, but they have to be very specific. But the slogan is really any unitary Jordan algebra with sufficiently many idempotents is in some sense a matrix algebra. So really what we see is this Peirce decomposition, this decomposing with idempotents proves some very powerful results, at least in the theory of Jordan algebras. So maybe it's worthwhile considering this as a defining axiom of a new class of algebras. And in that, what happens then is that you really get into the realm of axial algebras that have a different origin. But for this story, I want to kind of use this as a starting point. So what is this definition? We say that we pick any, just pick an element of K. Let's say it's also different from 0 and 1. And we ask that we have an algebra A with a generated set X, such that every A in this generating set is an idempotent. It is diagonalizable with precisely 3 eigenvalues, where this eta is fixed for every A, because we fixed it in the beginning. And the eigenspaces of LA satisfy the Peirce decomposition, where eta plays a role of 1/2. What do I mean by that is essentially that if I take any A in X now, that the eta eigenspace, so the eta eigenspace will be here, so A eta times A1 plus A0 will then have to be contained in A eta, right? Essentially, you can see that this is just saying, oh, as an axiom, I require that I have a lot of decompositions by idempotents in my axial algebra. I should have sufficiently many, in the sense that I should have so many that I kind of generate the entire algebra. Otherwise, I could just add orthogonal components to my algebra, which have nothing to do with these idempotents, and then you run into trouble if you want to start classifying them, right? Then a little extra condition, which is maybe a little more technical, or sorry for the constant sliding. I don't know what's happening. A little technical condition is that I have to ask that the idempotents are sufficiently small. I can see, for example, Vladimir Tkachev, who knows that when the idempotent is sufficiently small, then it's definitely primitive. But this primitivity is sort of an algebraic way of saying I want my idempotent to be sufficiently small. This just makes the objects easier to work with. And essentially, if we do not ask this, then we don't have that many results. That's kind of the idea. What does that mean? It's essentially like if I have an element that is a 1 eigenvector, so A times V is equal to 1 times V, then V should actually be just A up to a scalar. In other words, V should be equal to up to A to a scalar, but this is as small as possible, right? Because A times A is already equal to 1 times A, of course. A similar kind of notion of primitivity is happens in the Jordan context as well, where primitivity means that you cannot write A as the sum of two other orthogonal idempotents. But in some sense, the primitivity condition we require here, so this A times V implies that V is equal to A up to a scalar, is much, much stronger, or well, at least stronger than this orthogonal, like requiring that it does not have an orthogonal decomposition. And then the question is, like, does this actually provide anything interesting? Does it provide anything other than Jordan algebras? And the answer is yes, of course. Otherwise, I wouldn't be here speaking about these objects. But the examples came before the definition of a primitive axial algebra of Jordan type. So this definition is from 2015, and the first example of such objects which are not Jordan were already given in 2003. So in some sense, the examples of such things motivated the definition. And the examples are so-called Matsuo algebras, so the other type of object I mentioned in the title of my talk. We're going to talk about them. Maybe a small word from where they arose. They arose in the context of vertex operator algebras, where Atsushi Matsuo actually noticed the existence of them within the two-graded component of certain 1-0 vertex operator algebras. And then kind of try to see which kinds of three transposition groups arose from there. So to introduce Matsuo algebras properly, I'll first have to introduce three transposition groups, which were defined by Fisher in 1964. And actually, the finite irreducible case of these things was already classified in 1969 by Fisher. But anyway, a three transposition group is just a group G with a subset D, such that, first of all, we have two sort of non-degeneracy conditions. Again, D has to generate the group, which, I mean, of course, otherwise I could just take a direct product with another group that has entirely nothing to do with it and get a new three transposition group. This is not something we desire, of course. And then the first is that, well, the group is, the set is G stable, so that G has a natural action on this set. So if we have some set that generates G, we could try to make it a normal subset. But the third condition is actually the most relevant one. So essentially, we ask that for every element of our subset that the order is 2. So this is a subset of involutions or transpositions, whatever you want to call them. And then you ask that the product of any two elements has order at most 3. This is kind of a weird condition, but Fisher used actually just these definitions to find find 3 sporadic finite simple groups. So it turns out that even though it maybe looks weird at first, it's quite a powerful tool. And of course, there are some easy examples, right? If I take the symmetric group on n letters, and I just take the set of transpositions, right? So the set of elements that just swap 2 letters, then I know that the product of 2 such transpositions is either equal to a 3 cycle, or the two transpositions commute. So I know that if I have ij and I multiply it with lk, then either I can say this is equal to ijk if L is equal to k. What's happening? Yeah, L is equal to k, or it has order 2. Because then the two transpositions commute if they don't have any common elements, right? I might be wrong here in saying that ijlk is equal to ijk if L is k, L is j. I didn't compute this. It might be some other, whatever. It doesn't really matter. But this is sort of the first example you can think of if you see a 3 transposition group. Another thing that maybe is less well known, but still pretty well known, is that Sn is actually a Weil group of a simply laced root system. And it turns out that any other simply laced Weil group is actually a 3 transposition group where the D is the conjugacy class of reflections. If you know what a Weil group is, if you don't know what a Weil group is, it's essentially the reflection group of some combinatorial object. If you don't know what simply laced means, but you do know what a Weil group is, then you've maybe already seen the term type ADE. That's essentially what it means. So it's type ADE of Weil, or you can say that all roots of phi have the same length. That's another way of saying. A third example, which is also quite easy, is a subgroup of the affine group, essentially. It's on 3 of the affine group of order 3, sorry. So what happens here is that you just take the vector space F3 to the end, and then you extend it by the action of minus the identity on this vector space. And it turns out that, and you can again compute this by yourself if you want to, but it's quite easy to see that all such elements are actually involutions in this group, and that the order of any of these two has order precisely 3. So this is something that makes the third example quite different from the other two, in the sense that the product of any two elements of D is in this case an element of order 3. While in the first and the second case, you have many different elements of D that commute. So where the order of the product is 2. This is quite a special property. Such groups are called groups of Moufang type, if I'm not mistaken. But I mean, these are kind of just the 3 basic examples that you can think of when you think of a 3 transposition group. There are, of course, many other examples, but in some sense, you can think of either symplectic groups over the field of order 2, or special unitary groups over the field of order 4, or orthogonal groups over fields of order 3 or 2. These are kind of sort of the classical groups, which I will not go into because we will not need them in the talk. But there are many more 3 transposition groups than the ones I've given here. These are just to get a feel for the object. So the finite irreducible case was classified by Fisher in '69 in lecture notes, which have since disappeared. If anybody knows where these lecture notes are, I mean the Warwick lecture notes, I would be happy to have a copy of those. So here's a shout out to anyone who can deliver me a copy of those. But then the general case, so the possibly reducible case, and and also the infinite case was classified by Jonathan Hall and Hans Kuipers in 95. So that's 26 years later. That's quite an achievement as well. We're going to work with these three transposition groups in a sort of pictorial way. Why is that? Because essentially it makes it easier to work with. That's the reason. And I'll kind of outline how you can do this by whenever you have elements that have order 3, they essentially come in triples. So for example, here I know that I have the conjugate of 1, 2, sorry, the conjugate of 1, 2 by 1, 3, well, it's just equal to the transposition 2, 3. And this is the way you can kind of associate a picture to it by saying through every triple that I have, you can also check here that any 2 points on this thing, if I conjugate one with the other, I get the third. And this way you can get a sort of this picture where any 2 elements that are not connected by a line have order 2. So here you see that, for example, 1, 3 and 2, 4, they are not connected by a line because they commute. You can do the same for the 3-dimensional space of order 3. So that's the third example I gave, but then especially in 3 coordinates, where, for example, 0, 0 actually means the element 0, 0 minus the identity, right? And then you can check if I conjugate 1, 0 minus the identity with 0, 0 minus the identity, I actually get minus 1, 0 minus the identity. And I've drawn all the lines here, and as you can see, it's quite a messy picture. So in the future, I'll just draw it as such, like as a grid. That doesn't mean there's no lines. The other lines don't show up, but it's just a bit more of a nice way of describing it, because this is kind of confusing and chaotic. But it only happens once more in the slides, and then I'll tell you what happens exactly. Okay, we finally come to the definition of a Matsuo algebra. I'm sorry that it's taken this long, but whenever I have a 3 transposition group, and I can take eta, and I have not written it on the slide, but I can take eta and k without 0 and 1 again, then the Matsuo algebra is an algebra with with basis D as a vector space. So the basis elements are precisely indexed by elements of D. And I require that each basis element is an idempotent, that whenever the 2 transpositions commute, their product is 0. And whenever the order of these 2 transpositions, the order of the product is 3, then I have this weird linear combination of the 3 elements, where essentially it just uses the only 3 points on the line here. Okay. When eta is equal to 1/2, I'll just write MGD, and that's kind of the most important case to us, because that's where also the Jordan algebras live, of course, when eta is equal to 1/2. Like I said, there are examples of these axial algebras of Jordan type. This was proven in 2015, namely that the pair M eta GD, D is always a primitive axial algebra of Jordan type eta for any 3 transposition group, and then I should have written GD. And in that same paper, they actually also proved that as long as the parameter eta is not equal to 1/2, then any primitive axial algebra of Jordan type is a quotient of a Matsuo algebra. But it turns out that this 1/2 case is really an exceptional case in this theory. It's like somehow everything goes bonkers there. And there's good reasons for that, as some of you probably well know. And I'll talk about that a little bit more later. But in case we're working in the case 1/2, then we know that if the characteristic is not 3 and our Matsuo algebra is Jordan, then we only have one infinite family and one exception of 3 transposition groups that occur. So that means that many non-Jordan Matsuo algebras exist. And in fact, many Jordan algebras are also not quotients of Matsuo algebras in any way. The characteristic 3 assumption here is not really necessary. It's just that all I care about right now is characteristic different from 3, but the characteristic 3 case was actually classified by Yabe in a paper that caught an error, and I think the paper itself is from 2018, but I might be wrong. But the goal is then, of course, okay, we have this eta different from 1/2, where everything kind of seems to behave very rigidly, very combinatorially in this 3 transposition group setting. And in the 1/2 case, we have a sort of dichotomy of a Jordan case where a certain polynomial identity of low degree is satisfied, and we have these Matsuo algebras, and there is some overlap, but not much, and it's not clear how. And of course, the question is then, what is the difference between those two classes? But maybe first a small interlude on why 1/2 is kind of special. Suppose we have an axial algebra of Jordan type eta, and we have non-zero derivations in this algebra. So this kind of tells you that you have, at least in characteristic 0, if the derivation algebra is non-zero, this means you have a positive dimensional automorphism group. So that's why I say automorphism groups, but I mean, to me, they're kind of synonymous in some sense. But then you necessarily need to have that the parameter eta is equal to 1/2. And it's quite easy. It's not, nothing really happens. So suppose we have a non-zero derivation, and we know that X, so our set of idempotents, X, generates the entire algebra. That means that if this derivation is 0 on a generating set, then it's 0 everywhere, of course, by just using the Leibniz rule over and over again. But then again, by the Leibniz rule, we know that, well, dA squared is equal to a dA plus dAA, right? That's sort of that's just applying the Leibniz rule to this thing. But this is equal to dA because a squared is an idempotent. A is an idempotent. And because of commutativity, this is equal to 2a dA. Because we assume that dA is not equal to 0, this is only possible when dA is a 1/2 eigenvector, right? And we only asked for at most 3 eigenvalues, so 1, 0, or eta, and the only possibility then is that eta is equal to 1/2. So this kind of tells you that when the parameter eta is different from 1/2, the only thing you can have is finite automorphism groups. While in parameter 1/2, some continuity is allowed, essentially. And it turns out that there is some sort of converse to this statement as well. It turns out that if you take any primitive axial algebra of Jordan type 1/2, and if I ask that any non-trivial idempotent in a subalgebra generated by 2 of our axes satisfies the Peirce decomposition in the bigger algebra, this is only possible if and only if a map given by this assignment is a derivation of the algebra. So this assignment is essentially saying that I take the commutator of LA and LB, right? That's this map DAB is just taking the commutator of the left multiplication operator A with the left multiplication operator of B. And of course, in the Jordan algebra case, any idempotent satisfies the Peirce decomposition. So this tells you that this DAB is always a derivation in the Jordan case, which you can prove by other means as well, just by brute forcing it from the polynomial law, from the Jordan identity, I mean. But here it says that in this larger setting of axial algebras, you kind of have to have an algebraic condition on this very combinatorial or geometric flavor of saying that any non-trivial idempotent has to satisfy this Peirce decomposition. And it turns out that if it doesn't, so if DAB is not a derivation, then you can find precisely 3 non-trivial idempotents in this subalgebra that satisfy the Peirce decomposition. 3, no more, no less. Which is kind of special because that kind of is sort of similar to the fact that here you always have 3 points on a line in the Matsuo algebra case, and that's essentially where this 3 comes from. So this kind of tells you that the Jordan case and the Matsuo case are very far apart in some sense.
Yeah, Jari,
Yes.
excuse me for interrupting. Okay, just to be more precise, what do you mean satisfies the Peirce decomposition? Are the fusion rules or some decomposition at all, or what do you mean?
Yeah, I mean that if I take any non-trivial idempotent in in the subalgebra AB, then in A, the left multiplication operator. So suppose I have any non-trivial idempotent E here. It satisfies the Peirce decomposition if LE going from A to A is diagonalizable with eigenvalues 0, 0, 1, and 1/2. And of course, the eigenspaces belonging to these eigenvalues should actually also satisfy the same fusion rules. But I mean, I haven't.
Thank you. Okay, so I understand now. Okay.
Yeah,
so it should be.
Yeah, I haven't introduced fusion rules, and that's why I say satisfy.
No. Okay, so just to be.
Yeah, but yeah, this is essentially what it says. So it says that actually I have more than just the elements in X that satisfy this decomposition. Okay, so I was on the second point. If DAB is not a derivation, precisely 3 non-trivial idempotent, and then if it's a derivation for all elements in my generating set. So for all pairs of elements in my generating set, and the characteristic is not 3, then A turns out to be a Jordan algebra. So this kind of really tells you the difference between Jordan algebras and Matsuo algebra. And then with this philosophy in mind, you can kind of think, okay, so maybe the size of the derivation algebra of a Matsuo algebra kind of tells you how close it is to being Jordan. Not only that, but it might help you with finding some other examples of primitive axial algebras of Jordan type, which is something I haven't mentioned yet, but up until this year, the only non-trivial primitive axial algebras of Jordan type that were known were either Jordan algebras or Matsuo algebras, but it turns out that you can have more things than that. But essentially, we want to know what this derivation algebra is. That's our goal now. And the Leibniz rule is a linear rule, right? We can just essentially knowing or determining whether a linear map is a derivation is just solving a system of equations, namely by taking a basis and just solving the Leibniz rule for all pairs of this basis. Here we have a really nice canonical basis, namely just D, the transpositions of the Matsuo algebra. And then you can start calculating and you get a really ugly set of equations, which is given by these 6 families. And I implore you not to think too much about what this precisely means, but really these 5 first families kind of give you something quite special. They're local in the sense that the elements involved only occur in like a 3-generated subgroup of the 3 transposition group, right? You only use A, B, and C in all of these equations, where in the last equation you kind of have something that sums over the entire group. So that's more or less not so local. That's a really global statement. And what you can try to do is, like, if you think that many Matsuo algebras should have no derivations at all, you might think that the first 5 relations should be sufficient, or the first 5 families of relations might be sufficient to actually determine that there can be no derivations at all. And that's precisely what we'll do. But we'll do this then in the 4-generated case. And if it holds in a local subalgebra, then of course, using only these 5 families of relations, then we can also kind of conclude that for any larger algebras, there can be no derivations. Or for any larger 3 transposition groups. And that's why we kind of need the 4-generated case of 3 transposition groups. So if I have a 3 transposition group, I know that it's generated by 4 elements of D, but no less, because if I have less than 4 elements, then I can get S4 or 3⁵ colon 2. So that's the 2 examples I gave right here. But if I have 4 elements, then they're of central type. And if you don't know what that means, then you can think isomorphic too, but I mean, it's not entirely accurate. Then they're either equal to S5 to the Weil group of type D4, to this 3⁵ S4, which we'll talk about a little more later. Some special unitary group with an extension, whatever that means. This, this should be 3² too. This 3⁵ 2, that's like the 3-dimensional space. And then the Hall group denoted by 3⁵ colon 2. The Hall group is again something that you shouldn't really, if you don't know what it is, don't worry about it. It's just to be complete. The only one of these cases we'll discuss is number 5, because that, if we think about that pictorially, then we can think of the cube, and that will make things easier. So we'll prove that if we have a derivation of a Matsuo algebra, and A and B are in transpositions, such that they're contained in something that looks like 3⁵ colon 2, then actually dA of B will be 0. That's kind of the point. So we know from R5 that the coefficient at B of dA is equal to the coefficient of dAc at BC plus the coefficient of C at ACB. This looks really ugly, but the thing is that you can kind of represent this pictorially. So I've drawn the cube. There's some points missing here because they're inside of the cube. But I'll draw them later for some reason. But essentially what R5 says, you can represent this pictorially as saying dA at coefficient B is equal to dC at coefficient ACB plus the coefficient of dAc at dBc. This is kind of how I write it. But the thing is that just doing this, you can, by going through this picture and doing it once more, because what I've done here in this plane, I can actually repeat in this plane and in this plane, right? Through this slicing. So I can kind of push these equations back by applying twice R5. And then I get these 4 points. So the coefficient of this point at this point, the coefficient of this point at this point, which is still hidden, the coefficient of this point at this point, which is hidden, and the which is not hidden, and the coefficient of this point at that point, this point. Oh, and then we know that that we have actually another plane here, and there we can play the same game, saying that, well, if I apply the inverse of R5 in some sense, then these two give me the coefficient of this at this. And then I have another plane here that doesn't look like a plane, but it is, where I can again say that in total I get 2 times the coefficient of this and this. But the first relation we showed is that we saw over here is that the coefficient of A at B is equal to minus the coefficient at A at BA. If we then say, if we then look at this, then this is just equal to minus 2, the coefficient at this first node, and then the coefficient of DAB at this second node instead of the third node, because this is BA, this was B, and this was A, right? And then turns out that 3DAB is 0 after applying R1. This is kind of a picture that you can, that makes it easier to kind of see through the equations, because otherwise it's just a mess. And I've done this now for you for the 5th case, but you can do it actually for all 6 of these cases, where the 5th case is actually the easiest case. And then by kind of saying, okay, I know which possible elements can have non-zero derivations in a local perspective, I can try to extend this to a global perspective. And then it turns out that, well, of course, you have the Jordan examples, so Sn and 3 square colon 2. And you have actually an infinite family of exceptions where you take any simply laced root system of rank larger than 3, and you look at its action on the root lattice modulo 3. Where you also ask that the characteristic is not 3. The fact that you need to ask that the characteristic is not 3, like you can see it here, the 3 occurs. If 3 is equal to 0, I have concluded nothing. That's unfortunate. So really you have these Jordan cases, then you have one more infinite family of things that are not Jordan but do allow for non-zero derivations. And then you have a whole bunch of families that have no derivations and thus have a finite automorphism group. That's kind of what I wanted to say. So it turns out that these Jordan algebras tend to be very, very different from Matsuo algebras. Using this information of the derivation algebra, you can actually try to understand what the automorphism group is. But first, maybe this this weird example that I talked about, this extending the Weil group by the action on the root lattice. In the smallest case, it's this 3 to the 3rd colon S4. And then you kind of wonder, well, which 2 generated subalgebras, which correspond to lines here, actually allow for more Jordan type and idempotents. So which ones have this DAB as derivation? And it turns out that it's precisely the vertical length. This was observed the first actually by...
excuse me, can you just repeat, what do you mean by Jordan type idempotents?
Yeah, it's what I mentioned in the theorem. So in the theorem here is this satisfies the Peirce decomposition, right? I'm asking which two generated subalgebras have more non-trivial idempotents than just three, essentially, right? And I mean, two generated subalgebras, you can kind of correspond to lines in the pictures that I draw.
Because if it's sufficiently large, then it's Jordan-like. Okay.
Yeah,
So
exactly.
okay.
And then I'm asking, in this case, which two generated subalgebras actually give you more idempotents? So are such that this DAB is a derivation, and it turns out that it's precisely these vertical lines in the picture, and nothing else. And it turns out also that using this, we can kind of find a new model for this Matsuo algebra and describe the automorphism groups. So the automorphism group of the smallest one is just some classical group because it's Jordan algebra, the same for the second example. But what I care about is this exceptional examples. And it turns out that the automorphism group of this Matsuo algebra is just essentially the automorphism group of phi that acts on Gm to the rank of phi. You can wonder what exactly that means. Well, when the automorphism group or when a group acts on the torus, it also acts on the character lattice, if you know what that means. And the character lattice of rank phi, you can kind of canonically identify in this case with the root lattice. So the action here is essentially corresponds with the action of the automorphism group on the root lattice. That's essentially what happens. But that's interesting because also we know that the dimension of this automorphism group is actually precisely equal to the dimension of the Lie algebra. So we know that our automorphism groups are smooth in all of the cases, which in fact it might not be true in characteristic 3 because in small characteristics things usually go wrong. So I want to address some further questions since I hope that I still have time for like 2 minutes to just say this. So the thing is, what about characteristic 3? It turns out that this local perspective does not really work so well. And you could also wonder whether there are any Matsuo algebras with non-smooth automorphism groups. I've done some computer simulations and I didn't see any patterns that I could exploit yet, but I'm working on it. And then the second question is like, can we use this to find any new examples of primitive axial algebras of Jordan type? These are neither Jordan nor Matsuo. And the answer is yes, and that's joint work with Sergey Shpectorov. But I haven't had time to make a presentation about that yet, hence I've not talked about that yet. And then we've described automorphism groups of Matsuo algebras, but is there some way of extending this description to non-trivial quotients of Matsuo algebra? Because Matsuo algebras, because these exist and I don't have a good grasp of what they look like yet. But it's to kind of further explore this theory of axial algebras of Jordan type, it would be very beneficial. And it kind of looks like any primitive axial algebra of Jordan type has to be some sort of mixture of Jordan algebras and Matsuo algebras, but we're not entirely sure how and why. But the fact that you have this, that this is not a too wild of a class shows that it's still a powerful axiomatics, this idempotence structure. And that's kind of all I wanted to say. I hope you've learned something from this talk. And if there are any questions, you can ask them.
Thank you very much, Jari, for your nice talk.
Thank you for listening, by the way.
Other questions?
I'm a bit curious about the 6 relations, relations. Okay,
Yeah.
So can you just comment other, in a sense, should be independent, or what is a technique how to get there? Okay, what does it tell us? Okay. So,
That's the thing, I don't know. I find the sixth relation hard, so I just ignored it. And then it turns out for characteristic 3, that's sufficient. Yeah, it's for characteristic 3, it's sufficient, and it allows you to have this nice local perspective where you can just look at 4 generated subalgebras, and then you sort of work from there. But the sixth relation is just it enumerates over things that are orthogonal to A but not orthogonal to B. So like if I have A here and I know that B sits here, I'm essentially enumerating over so-called dual affine planes over so the E's I'm summing over in R6 are precisely these ones. And you're essentially enumerating over all dual affine planes of order 2 that the line AB is contained in. Equivalently, dual affine planes are subgroups of type S4. So this equation just enumerates over subgroups of type S4, but I don't know that much about subgroups of type S4 in arbitrary 3 transposition groups, so I cannot.
yeah, I see, and this is related to a specific combinatorial design, okay, like this.
Yeah.
If it will be a different design, say, okay, so is it easy also to get something? Okay, or so the first relations you just say, okay, maybe not all excluding R3. So it's just you evaluate some derivation at some point and you simplify it in a sense, right?
Yeah, exactly.
And you use this three transposition combinatorial design to get it simpler, so to speak. Okay,
Yes.
okay, but okay. I'm just
But there's no way
general.
There's no way of or at least I haven't found a way of simplifying this relation, because you could wonder if it decomposes into some equations that actually do, but I haven't found no way yet.
Okay, so but it's interesting still. Okay, so yes,
I've asked my computer to do it, and my computer says no. So in the sense that I wasn't able to work it out, not that it's impossible. But because it seems to be a bit redundant in characteristic different from 3, but it's definitely not redundant in characteristic 3. And that's kind of surprising to me. So in characteristic 3, this thing actually does play a giant role in determining the dimension of the Lie algebra of derivations. And I don't know why. I don't know why it happens to not play a huge role in characteristic different from 3. Maybe that's more fair to say.
Are there more questions?
Good morning, everyone. So first of all, thank you very much for this interesting talk. Then I just want to ask, could you give an example of a Matsuo algebra which is isomorphic to some commonly known algebras, like matrix or stuff like that?
Okay, so I mean, the Jordan algebras I can give you.
Yes.
The thing with the non-Jordan algebras, you just know them in terms of their basis of the theta between theta. But if there was any nice isomorphism, you know they exist within the stack, but there's reasons why they exist. But for example, I should have some yeah, if I take the Matsuo algebra as then it's essentially equal to the subalgebra of it's equal to the Jordan algebra given by matrices which with where the sum of the entries in every row and every column is 0. So n by n matrices where the sum of every the entries in every row and the entries in every column are 0. So this is the way you can think of Jordan algebras. And if you look at the Matsuo algebra from 3² : 2, so the smallest affine case, that is equal to the Hermitian 3×3 matrices, essentially, like the symmetric 3×3 matrices. This is the only thing I can give you. I'm sorry.
Okay, thank you very much. Yeah.
More questions?
If I may ask a question, thank you, Jari, for a very interesting talk. I have a sort of more question on the philosophical side. So reading your work and listening to you, this fact that Matsuo algebras that are not Jordan algebras have very few, I would say almost no automorphisms. I mean, they have a trivial derivation algebra. Is a bit in contrast to Jordan algebras that I view as algebras where you can have huge automorphism groups and derivations algebras. So these quotients you talk about in the end, maybe I missed it, but what kind of automorphism groups do you expect there?
So in general, they can be infinite. There is no, there are many Matsuo algebras where we know that the quotient is actually a Jordan algebra. There also exist Matsuo algebras where this is not the case. But essentially, who knows, anything might happen. So this is something I'm not entirely sure of. I do know from work with Sergey Shpectorov that essentially, like always, the structure of idempotents and hence the structure of the automorphism group will always be largest when you're working with a Jordan algebra. Otherwise, it looks like a continuous automorphism group where some 3 transposition group acts on it in a non-trivial way. How should I put this? It looks like a connected automorphism group extended by a 3 transposition group, but we don't even know whether this extension is split in any way. We can, yeah.
Cool, thanks.
I hope that clarifies the situation.
Yeah, that does. Thank you.
Maybe one more question. Okay, I guess there are no questions. So thank you, Jari, once again for your talk. Thank you for all the participants, and have a nice week. See you.
Bye.